Hello guys, I hope you all are doing well. Today we will be holding our first review session for the upcoming Orgo 2 Exam 2. And as usual, the structure of this review will be that we'll be going over a previous year's exam. In this case, it will be the Exam 2 of Spring 2019. And after that, we'll be going over a few multiple choice questions from the ACS Organic Chemistry Study Guide. So let's start. So part A is nomenclature, three questions, and we are asked to give the IUPAC name for each of these compounds. So as usual, the first thing we need to do for this compound is to identify the parent chain. So when we're looking for the parent chain, typically in the past, we would look for the group that had either the most number of carbons and or the group that had the highest priority groups. So in this case, when we look at this molecule, we notice right away that there are three sets of groups. So this is an aldehyde group. This is not a phenyl group actually. This is what you refer to as a benzyl group. Now a benzyl group is just a phenyl group but with an additional methylene group added to it. So in other words, just to draw it out, this is a phenyl group, and this is a benzyl group. So what we see here is there's a CH2 group right here that's also counted as part of this overall group, and that's precisely what we see here. So just wanted to put that as a side note just so that you guys would be aware of that. And now that we have that cleared, let's also talk about priority. So for these groups, according to the IUPAC nomenclature, it turns out that out of all of these groups, the aldehyde group is the highest priority. So typically in the IUPAC nomenclature, the priority of the group increases as you increase the oxidation number, or the number of bonds that a particular substituent has, which is also tied, to the number of bonds that a carbon atom that is a part of that substituent has with an oxygen atom. So in this case, we see that this carbon here has has a double bond with oxygen, and comparing that to the alcohol, that allows it to have a higher oxidation state as compared to the alcohol. So actually, if you were to compare the aldehyde to, say, a carboxylic acid group or carboxylate group, you would find that the carboxylic acid group would be considerably higher, higher in the priority in IUPAC nomenclature, precisely because of its higher oxidation. So just as a note, so when we go about doing the nomenclature, the first thing that we have to do, again, is to list out the parent chain. So since we identified the aldehyde as the main group, now we know that we have to start from our counting from here. So we go from that carbon to that carbon. Now again, we want to keep the priority of the group based on, so in this case, we would have to consider two paths. We could go this way or this way. Now, we can go in this direction because there are more carbons, so it allows us to also have a longer carbon chain. But alongside that, we also have an alcohol, which is also a high priority group. So now that we have the main chain down, let's do the numbering. So 1, 2, we start from the highest priority group, 4, 5, 6. So this is our numbering so far. And now that we have the parent chain down, we have it at least written out, we can write it in terms of a name as, let's start with the prefix. So since there's 6 carbons that are in the backbone of this chain, we would use the hex prefix. Now, since the aldehyde is the highest priority functional group in this chain, we would have to have a suffix hexanol. So what this is referring to is the Al suffix, is referring to the presence of an aldehyde in the parent chain. So now that we have the parent down, let's talk about the subs, or the substituents. So the first substituent that we have, well, we can just list out whatever we see. So at 4 we see the presence again of a benzyl group, and let me just remove that. And at the position number 6, we see a hydroxyl or hydroxy group. So now that we have the substituents listed, we also note that this benzyl group has a higher is first in the alphabetical order. So now that we have that also settled, we can write out the full name. So 4 benzyl 6 hydroxy hexanol. And that should be our final answer for this question. For question 2, we have another compound where this time we have 2 rings instead of just 1 ring, as we saw in the previous case. Now the question is, well, what is the parent chain again, right? That's the first step that we always resort to when we talk about the nomenclature. And it turns out that the parent chain is actually, can you guess? It is the ring that has the ketone on it. So the reason why it is this group is because, again, it follows the same line of reasoning for why we chose the aldehyde in the previous question, as I had explained earlier, because groups that have oxygens attached to the carbons have a higher priority than the groups that do not have oxygens attached to them, precisely because it has a higher oxidation. So just to keep that in mind, since we have that down, now the question is, where do we start numbering? So just like in the previous question, when we had started numbering from the carbon of the aldehyde, in the same way we start numbering from the carbonyl group. So we have this carbon listed as number 1. Now the question is, well, what about which direction do we go when we're numbering, since this is a cyclic molecule? So since the ring that has the carbonyl group is considered the parent chain, this whole substituent, this bromophenyl substituent, is actually is also subject to the same rules when it comes to numbering of substituents. So we want to make the numbering of this bromophenyl substituent as small as possible. So for that reason, we start counting in the counterclockwise direction, so to speak. So once we have that down, now we have the ordering of this ring of this parent chain, and when we look at the parent chain, let me just remove the previous highlighting. we see that there is a alkene or a double bond between carbons 5 and 6. So that affects how we name the parent chain. So since the location of the double bond affects the name, we have to incorporate that in our description of the parent chain. So another factor that also affects the parent chain's name is the presence of this carbonyl group. And this would actually be considered as a ketone, this particular structure, because there is a carbonyl group accompanied by two R substituents, so to speak. So because it's a ketone, because the parent chain has both a ketone and a alkene, we can actually refer to this as, since there's 6 carbons, this would be referred to as cyclohexanone. So the name, right, cyclo because it's a cyclic molecule, hex because there's 6 members, it's a 6-membered ring. The N is referring to the fact that there's a double bond, and the -one suffix is used to refer to the ketone that is present. But now there's also an additional specification that we do, namely that we have to specify where the alkene is. So since we always count our alkenes from the lowest number, in this case carbon 5, we list it as 5 cyclohexanone. So now that we have the parent name decided, let's look at the subs. So as I mentioned earlier, there is a bromophenol substituent, and it is a complex substituent, so we're going to have to incorporate parentheses. But in addition, we also have to account for the that additional bromine, the location of that bromine. So we start our counting from this carbon, since that's the carbon directly attached to the chain. And since we want to lower the substituent number of the bromine, we count counterclockwise, 4, 5, 6. So that means in order to denote the location of the bromine, we can use a number, that is position 3. Or alternatively, we could also use the notation meta, because this bromine substituent is 2 carbons away. It's actually separated by a carbon from the parent chain, or from the substituent, on this on carbon 1, right? So this substituent that's at carbon 3 is 1 carbon away from the substituent on carbon 1, which is actually the parent chain. So we can use the meta description as well. So that is up to you how you write that. So the last detail that we have to add is that we have to talk about where this complex substituent is with respect to the parent chain. So since this substituent is attached to carbon 2, we can apply that descriptor there. And now we have our name, 2, 3, bromophenol, 5, cyclohexanone. And, or alternatively, we can put meta in this, in lieu of the number 3. So that is how we solve for the name for this particular compound. Now for question 3, again we have a 2-ring system, but we can apply the same thought process to first identify the parent chain. Now in this case, since we have a so when we identify our substituents, we see a carboxylic acid group there. We see a ketone here, or more specifically, it's yes, it is a ketone group, but more specifically, it is a oxo group, and it falls within that. So now that we have the substituents listed, let's try to decide whether or not the ring on the left or the ring on the right has the higher priority. And again, we're using the same principle as we had used earlier. So the substituent that has the most, I'm just rewriting this substituent, so I'm just going to, just so it's easier to understand, I just rewrote that. So we see that this carbon here for this substituent is attached to 2 carbons, so it has a higher oxidation state than this oxo group. So that means that the ring that the carboxylic acid group is attached to, namely this benzene ring, is the parent chain. So now that we have the parent chain decided, let's do our numbering. So we start from the highest priority group, and now that we're counting, we want to reduce the substituent number of this entire ring, which is attached to the benzene ring. So we go in the clockwise direction when we're counting. And now that we have that numbering down, let's also just quickly figure out the numbering of the oxo group, or sorry, the ring. So when we see this ring, we see that, again, we start from the carbon that's directly attached to the parent chain, and then we count in the clockwise direction so we can get the lowest substituent number for the oxo group, namely 2. So now that we have the numbering down, now it's just a matter of getting the specific names. So we see that this the benzene ring is attached to, again, the carboxylic acid group, and that is specifically, that combination is referred to as benzoic acid. Now that we have the parent chain decided, let's look at the subs. So again, at 1, since the carboxylic acid group is already a part of the overall parent chain, we're not treating that as a sub. Really, the only sub there is this entire ring, this ring right here. So that means that we start with the location of the location of the substituent with respect to the parent chain, which is at carbon 3, this carbon right here. So now that we have that down, let's get into the specifics of this complex substituent. So since this is an oxo group, we can say that this is an oxo group, but it's also tied with respect to since this is not the parent chain, we can refer to this ring as a cyclohexyl substituent, right? Cyclohexyl. But since there is an oxo group at carbon number 2, we have to also specify that, and we can do so by saying 2-oxo-cyclohexyl. Now that we have the substituent down, there's one more thing I forgot. And again, if we compare the carboxylic acid group to the oxo group, what do we note? Or specifically, or actually this is a better way of putting it, if we compare carbon atoms 1 and 3, what can we say about the configuration of the cyclohexyl group, the 2-oxo-cyclohexyl group? So we find that it's 1 carbon away from the carboxylic acid group, which is part of the main chain, which is why we're not considering it as a substituent. So since it's separated by 1 carbon, we can use the meta description as another option. Again, it's up to you whether or not you want to use 3-2-oxocyclohexyl or meta, 2-oxocyclohexyl. It's up to your discretion. And again, we can replace this with a meta. Let me just note that earlier as well. We can interchange between them. It's up to your choice. So again, the YL for the cyclohexyl, it's just again indicating a substituent. So substituent. So now with that, we are able to finally answer this question. Now that we have finished part A with nomenclature, now we're at part B, so the facts section, and we're given a set of questions where we have to rank sets of compounds based on various properties. So for question 1, we're given a set of compounds and we're asked to label the molecules as either aromatic, anti-aromatic, or non-aromatic. And an important fact here is that we're allowed to assume that they are all planar. So this will play an important role in deciding whether or not these molecules are aromatic, anti-aromatic, or non-aromatic. And before we dive into them, the first thing that we need to go over are Huckel's rules for determining aromaticity. And so the first thing is that we need to understand, is this molecule, for a given molecule, is that to determine whether or not that is of an aromatic or anti-aromatic nature, we need to see if, first, that is it cyclic. Second is it conjugated? So can all the atoms in that ring participate in pi bonding to form a pi ring system, basically? So as a basic example, in benzene, when you have a set of bonds like this, all of these carbon atoms are in conjugation because they are all sp2 hybridized, and they are able to form this network of electrons, which is basically called a conjugated ring. So that is an important criteria when we are evaluating whether or not a ring is conjugated. One deal breaker for deciding whether or not something is conjugated or not is if for sure at least one atom in that ring is sp3 hybridized. Because if an atom in the ring is sp3 hybridized, then you can't form that conjugated ring. Because in an sp3 configuration, you are unable to form a double bond if you're dealing with an element that follows the octet rule. Now, whenever it comes to dealing with heteroatoms, as we will soon see, it gets a little trickier because these heteroatoms can have the option of sometimes being in an sp2 configuration or sp3 configuration. Well, specifically a few, not all of them, but we will go over the examples. So it's not as easy to check off a criteria that's as easy to check off as, say, whether or not that molecule is cyclic. So that's the second criteria. Now the third criteria is that the molecule is planar. And here's where the assumption comes in. Since we are allowed to assume that all of these molecules are planar, then we know for sure that we can tick that box off for all four of these molecules. Now the fourth one is that if properties 1 to 3 are, if properties 1 to 3 are all ticked off, then we can say that if there are 4n electrons, then we have, actually I'll write this a little bit more concisely. 4n electrons, we have a anti-aromatic system. If we have 4n plus 2 pi electrons, we have a aromatic system. That is, again, assuming that all three of the previous conditions are met. So that is an important note. And if we have these rules described properly, then if we're able to, meet all these conditions, then we can describe these systems as either aromatic or anti-aromatic. But if one of these conditions is violated, then we are forced to say that the molecule is non-aromatic. For the molecule on the left, let's start applying Huckel's rules to see how we can go about and classify this molecule. So we see right away that it is indeed cyclic, and it is planar because of our assumption. And so the question is it conjugated? So we see right here that we have a pair of electrons on this carbon right here. So we have a carbanion. And the question is, well, is this pair of electrons part of the pi system? And it is actually indeed part of the pi system, because if you're able to visualize the one atom that is not present, there is a hydrogen. And that hydrogen actually can form a planar configuration with the other remaining. So let's say this is the carbon atom, right? I'm referring to this carbon atom right here. It's just another view of it. And we have this hydrogen here, and it's attached to the other carbons. So this carbon right here, the lone pairs that are on that carbon can actually form a pi bond orbital, a p orbital that, that will actually work in conjugation with the other p orbitals around it. Sorry about that. So what that means is that this pair of electrons can indeed be counted as a pair of pi electrons. So we note that down as well. Now we're up to 6 pi electrons. And because if we also count these two, right, the two from each of these double bonds, which I've noted in red dots. Now the question is, what about the lone pairs on the sulfur heteroatom? And for the sulfur heteroatom, it turns out, well, for any heteroatom actually, if you have more than one pair of lone pairs on that heteroatom, only one of those could potentially serve as a p orbital. That it could only work. That could only form a p orbital, because only one p orbital is needed in order for that atom to join that ring, that conjugated pi ring. So let's say, for example, we don't know yet if this lone pair of pi electrons is actually part of the system. So we can do two cases. Let's consider two cases. So case one, let's actually treat these two as pi electrons. And when we do that, we get a total of 8 pi electrons. But there's one more thing. If we consider this as a pair of 8 pi electrons, then say if we take resonance into consideration, then the actual hybridization of this sulfur atom is sp2, right? So if that is sp2, then that means that the entire ring is capable of, of conjugation. So the ring is indeed conjugated. And if it's conjugated, then the first three conditions of Huckel's rule are met. So what that means is now we can look at the number of pi electrons. There are 8 pi electrons, and since 8 is an integer multiple of 4, the 4n plus the 4n rule is met. And that means that by Huckel's rules we get an anti-aromatic structure. That is for case 1. Remember, this is a hypothetical scenario. For case 2, I'm going to just do this in blue so I don't confuse anyone. Now let's pretend that these are not lone pairs, right? So now we have 6 pi electrons, but moreover, since there are 2 localized lone pairs now on that sulfur atom, and there are 2 single bonds that are attached to that sulfur atom, that now attains a hybridization of sp3. So if there's a hybridization of sp3, then the ring is no longer entirely conjugated, right? Because all the atoms need to be sp2 hybridized. So that means that we have violated one of Huckel's rules, and therefore we have a non-aromatic structure. So now we have a choice, non-aromatic or anti-aromatic. So this is where energies come into play. So remember that anti-aromatic, aromatic, and non-aromatic structures have 3 different relative energies. So at the top, anti-aromatic molecules have the highest energy. Non-aromatic molecules have the second highest energy. And the molecules that have the least energy are aromatic molecules. So nature always wants to have the lowest energy configuration. So a molecule wants the lowest energy configuration. So if a molecule had to decide between anti-aromatic and non-aromatic, it would choose non-aromatic because it is the lower energy state, right? It's lower in energy than anti-aromatic. So that means that the molecule would actually be, since it's flexible, it will choose the option that is the lower energy option. And in that case, we have non-aromatic as our answer for the first one. So for the second molecule, we have, let's apply the conditions again. It's cyclic, it's planar, and let's count our pi electrons, right? We have 4 from the double bonds. Since there are no lone pairs on the carbocation, we don't have to worry about that. In addition, that carbocation is also sp2 hybridized. And now let's look at the boron. See, now boron is a special molecule, a special element, because when it forms bonds, it only forms bonds, and it only can form 3 bonds. So that means that it will always have an sp2 configuration. So that the implication of that is that the entire ring, right, all of the atoms are indeed conjugated. So if there are no additional pi electrons, then if we look at 4n electrons, that is an integer multiple of 4, right? So 4 times n, and n being 1 in this case, gives us 4 electrons in total. And so that means that we have a anti-aromatic structure because the 4n rule was met. Now, for the third structure, we have a ring where there are I'm just noting out the pi electrons on the double bonds. So let's try the rules again. It is indeed the molecule is cyclic, it's planar, and when we look at each one of these, let's first look, there's 2 heteroatoms, so we have to look at each one of them first. So nitrogen, right? So nitrogen, it has a formal charge of 0, and this question is, can this lone pair be a part of the overall conjugated pi ring? And it turns out that in this case, that lone pair can't participate. And the reason for that is that that nitrogen is already engaged in, it already has its p orbital employed in a double bond here, right? So for example, when we look back at this carbon ion right here, for the first example on the left, that carbon was not involved in any sort of double bond, right? So it had a lone pair of electrons that were free to engage in a conjugated pi ring. So that was why we were able to treat this pair of electrons as a part of the conjugated pi ring. But in this case, the p orbital is already employed, right? And in that p orbital, the lone pair of electrons is not in that p orbital. So that means that indeed this pair of electrons is localized. So since there are 3 electron domains on that nitrogen must be sp2 hybridized. Okay, so we've got that one settled. Now let's look at the oxygen. So in the case of the oxygen, we have a situation similar to the sulfur. So this oxygen can potentially give one lone pair to the overall pi ring system. But we have to consider energetics again, right? So let's consider 2 cases like we did before for the first case, for the first molecule that we worked on. In case 1, let's treat this pair of electrons as part of the pi system, right? So that means that in total there are 6 pi electrons. And if this is part of the pi system, then there are only 3 localized electron domains on that oxygen, right? 1 from the lone pair and 2 from the 2 single bonds that are attached to the oxygen. So if there are 3 electron domains in that scenario, we would have an sp2 configuration on that oxygen. So it is indeed conjugated. And it's also cyclic and planar. So if there's 6 pi electrons, it turns out, I'm just going to remove these, that 6, you can get 6 from doing 4 times 1 plus 2 is equal to 6, where n is equal to 1. Since the 4n plus 2 rule is met, then we can say that this molecule, for this specific scenario, would be aromatic, right? But let's say for case 2 that we didn't consider these as part of the pi system. Then we would have 4 pi electrons. But another important thing is that now there are 4 localized electron domains, right? 2 from the 2 from the oxygen and 2 from the single bonds. So that gives us an sp3 hybridization, and bam, the conjugated condition fails, right? Because now one of the atoms is sp3 hybridized. So that means we are left with non-aromatic. Now the question is, do we want non-aromatic or aromatic? So let's look back up at our diagram right here. So in the diagram, we see that aromatic is a lower energy than non-aromatic. And again, since the molecule wants to be in the lowest energy position possible, it will prefer aromatic, right? So aromatic is our final answer. Now for the last one, the last problem, we have a molecule where there is a positive charge on an oxygen, and there is also a possibility for resonance. So if we draw out the resonance structure of this molecule, where we move this guy back up, this pair of electrons, we are left with an OH group. And when we look at this molecule and both of its resonance forms, we find that yes, it is cyclic, it is planar, it is conjugated, because all of the atoms here, right, even the nitrogen in both scenarios, the lone pair right here is actually part of the pi system, because you can form a p orbital with that lone pair, while the hydrogen will be will be part of the sp2 orbital, and if that is counted as a lone pair along with these two guys, then we have 6 pi electrons. And that means that before we get to that, let's also discuss the configuration of this particular carbon. And we see that in both cases, in here there's only 3 electron domains, and here, since it's a carbocation, there's only 3 electron domains, so we're left with sp2 in either case. So that means that in fact all the atoms within the ring are sp2 hybridized and therefore conjugated. So because of that, right, because there is that room for sp2 hybridization around this molecule, that pi ring system can be formed. Now, another thing that we need to ask is about the total number of pi electrons. And since we had found that there were 6 pi electrons, and just like in the previous scenario, that meets the 4n plus 2 rule, that means that this is also aromatic. There are no choices. So with that, we have solved the first question. In the second question, we have a series of benzene compounds, and we're asked to rate them in order of an increasing rate in an electrophilic aromatic substitution, or, which is abbreviated as EAS, reaction. So for this reaction, we are asked to, since we're asked to rate these by an increasing rate, the important thing to realize about an EAS reaction is that the more nucleophilic you can get it, the more, the higher, let me just write this down, the more nucleophilic the substrate, or what is the compound that we're working with, the higher the reaction rate. So how do we increase the nucleophilicity of each one of these, of a given molecule? We can do that by adding activating groups, or which is also referred to as an electron donating group. So and I abbreviate it as EDG. So now that we have the guiding principle down, let's look at each one of these molecules. So we see that there's a benzene ring in each one of them, and in the substituent of concern is each of these substituents. We don't care about the carbon atoms that are at the bottom because they're all the same in all 3 molecules, and they don't provide any special contribution to the reactivity of the molecule. However, if we examine each one of these groups, then we're capable of deciding which one has an EDG or an EWG, or electron withdrawing group. Electron withdrawing groups do the opposite of electron donating groups. They withdraw electron density from the pi system, and that causes the ring to be deactivated. And when the ring is deactivated, to be more deactivated, then that actually decreases the rate of reaction in an EAS reaction. Now, the opposite trend occurs in a NAS, or nucleophilic aromatic substitution reaction, but we'll get to that later. So for this first substituent on the left, we have a nitrogen attached to 2 methyl groups and 2 carbon atoms. And that means that since if we assign it a formal charge, it would be a full-on positive charge, because there are 4 single bonds, and the valence of this nitrogen is 5. So that means that there would be 5 minus 4 equals 1, a positive 1 or plus 1 formal charge. And if we look at the second substituent, we see that there is a amide, right? And this amide has a carbon which has a partial positive charge because of the electronegativity difference between the carbon and oxygen and the carbon and nitrogen. So there is a partial positive charge here. And when we look at this nitrogen here, we see that there's actually a lone pair at that nitrogen because there is a formal charge of 0 there. So what this means is that there would be basically a pair of electrons that can potentially engage in resonance with the rest of this benzene ring. And this is referred to, this makes this substituent a resonance electron donating group, right? Because it's capable of donating electron density to this benzene ring via resonance. So for the first two, we have to ask, well, what are these two groups? Turns out that since the nitrogen and the carbon here are both electron deficient, they want more electrons. So they're going to try to take electron density from the benzene, and this makes them, since there are no pi bonds or resonance involved, it would make these two inductive electron withdrawing groups. And so if these two are both inductive electron withdrawing groups, that means that they actually deactivate the neighboring benzene ring, while this molecule, the substituent, actually causes the benzene ring to be activated, so to have a higher nucleophilicity. So if this molecule has a higher nucleophilicity, then it will have the highest reaction rate in an in an EAS reaction. So that gives it the fastest rate, since the other two actually cause the ring to deactivate. Now the question is, which ring, for the remaining two options, which ring deactivates more, the one on the left or one on the right? Well, it turns out that since the nitrogen has a full-on formal positive charge, while the one on the right, the carbon, has only a partial positive charge, the nitrogen will be more electron deficient and therefore a stronger inductive electron withdrawing group. And in that case, this molecule will be more deactivated than this molecule. And if that's the case, then we know that this molecule will have a slower rate than this molecule. So, based on that fact, we can say safely that this is the slowest rate and this is the next slowest rate. And with that, we have ranked this series. For question 3, we are given a set of molecules and we're asked to rank the compounds in order of increasing reactivity in an SN1 process. Now, in an SN1 process, the rate limiting step of this process is the formation of the carbocation upon the removal of the leaving group. And in this case, in all three of these compounds, that leaving group is the bromine group. So if we remove the bromine group, then we are left with a secondary carbocation. But not only that, we are left with a conjugated secondary carbocation. So that allows it to be in resonance. So because of this idea of conjugation, we have to consider the possibility of, well, is it possible that these structures might be aromatic, anti-aromatic, or non-aromatic? And the reason why that's an important question is because all three of these structures, if they're aromatic or anti-aromatic or non-aromatic, that can greatly affect the stability of this carbocation, far more than just the fact that it's secondary and that it's conjugate is whether or not it's aromatic or non-aromatic or anti-aromatic. These three states have noticeably different energies, and along with that, noticeably different stabilities. So if these carbocations have different stabilities, that can affect whether or not it can affect the reactivity of the SN1 process. If one carbocation is more stable than another carbocation, then the first carbocation can actually have a better reactivity because that is a more stable transition state, or more stable intermediate, So what we're trying to find here is if we're able to classify, if these three different molecules have different aromaticity states, so to speak, then that will allow them, we can easily determine which ones will be more stable and therefore more reactive. So let's apply Huckel's rules to these three molecules and see what we get out of it. So for the first one on the left, we see that it is indeed cyclic. We see that it is not conjugated though, because although there is a carbocation that is sp2 hybridized, and these guys are also sp2 hybridized, what about this carbon? This carbon has two hydrogens, right? So it can't engage in resonance, and that makes it an sp3 hybridized carbon. So, well, I'm pointing to the hydrogen there, my bad. So to the carbon. And that means that this ring is not conjugated. So right away, we know that this ring will be what? Non-aromatic. It's not our final answer, it's just, that's why I didn't put in the box. But it's part of the process. So for the second molecule, we see that it is cyclic. We look at all of the atoms and we see that they are all either part of a double bond or they are a carbocation. And we know that all of these must then be sp2 hybridized and therefore open to forming a conjugated ring, conjugated pi ring. So we can also check off that box. Now, what about the fact that it's planar? Well, since all of these are sp2 hybridized, then they must be planar, right? They don't have any atoms that are sticking out into a third dimension, right? So it's a planar molecule. Now, let's count the number of pi electrons in this molecule. So if we do that, we have 1, 2, 3, 4, 5, 6. There are 6 pi electrons in this molecule. And remember from earlier, 6, you can get the number 6 by doing 4 times an integer, which is in this case 1, plus 2, which is 6. And since it follows the 4n plus 1 formula, we have an aromatic situation here. We have an aromatic molecule. So that condition is met. So we have aromatic. So now let's look at the last molecule. So here we have a cyclic molecule. So check. We have conjugate. Well, yes, we do have conjugated because all of the carbon atoms are either in a double bond or they are carbocation. And we see that because they are all sp2 hybridized, they are planar. So let's count the number again, the number of pi electrons, and we have 4 pi electrons. So that is an integer multiple of 4 electrons. And so 4 times an integer, namely 1, gets you 4. So since it matches the 4n rule, we have anti-aromatic. So let's look at these. Since we're in a really good situation now because all three of these have different states. One is non-aromatic, one is aromatic, and one is anti-aromatic. So the energy hierarchy, right? We have anti-aromatic, non-aromatic, and aromatic. So since anti-aromatic is the highest energy state, we find that this guy right here will be the highest energy. And if that molecule has the highest energy, it is also the most unstable. And if it is the most unstable, then what does that mean? It means that the rate limiting step, namely the formation of this carbocation, will be very energetically unfavorable. So in terms of reactivity, the reactivity will be the lowest out of all three of these molecules. So that means that we can give this the ranking of 1. Now let's look at the first and the second molecules. So we see for the non-aromatic state is a higher energy than the aromatic state. So that means that that will be the second highest energy and therefore the second most unstable. So if it is the second most unstable, then it is still having a higher reactivity than the first case we saw. So now the remaining one is just 3, right? And that also makes sense because it is aromatic and therefore the lowest energy, so it is the most stable. And since it is the most stable, that rate limiting step is the most energetically favorable step. So that allows us to have the most reactivity when we are forming the carbocation for this molecule. So with that, we've answered question 3. For question 4, we are given a set of compounds. We're asked to rate them in order of increasing amount of hydrate that is present at equilibrium when they react with water. So what is the first thing we notice about all of these compounds? They are all either ketones or aldehydes. And so when ketones or aldehydes react with water, so I'm just going to show this as a general example, we get a hydrate group. Now the R's can be any arbitrary atom or group. It can be hydrogens, it can be actual carbons. This is just very arbitrary. I just placed it as R. It doesn't have to be a carbon, just to make that clear. So in this reaction, to shift the equilibrium, my bad. I meant to use an equilibrium sign here. So in order to shift the equilibrium more towards the hydrate product, we need to actually there are 2 factors that we can optimize in order to do that. So the first thing is that we can increase the partial positive charge on the carbon of the carbonyl. So this carbon right here, we can increase the partial positive charge because this reaction happens when the oxygen of the water molecule attacks this carbonyl carbon. That's how it is initiated. So if we're able to increase the electrophilicity of this particular carbon, then we're able to cause the reaction to increase the reactivity and thereby shift the equilibrium to the right. In addition, if we're able to reduce steric repulsion, then water molecules will be able to access this carbonyl carbon with less steric hindrance, and so the likelihood of it occurring, of the water molecule actually attacking this carbonyl carbon, also increases. So that also causes a shift to the right. So now that we have these two factors down, let's look at these molecules in particular and see what we can deduce about how they would behave in this sort of reaction. So when we look at the first two, we see there are chlorine substituents attached to the carbon atom that is adjacent to these carbonyl groups. And this chlorine plays a role in our attempt to solve this problem, because the chlorine serves as what? It serves as an inductive electron withdrawing group. It takes away electron density away from this carbon because of the electronegativity difference between the carbon at this carbonyl and the carbon at the carbon attached to the chlorine group. And because of that, it causes the partial positive charge to increase at both of these carbons. So when we look at case 3, we see that that is definitely not there, right? We see that there are no such groups that help us to increase the partial positive charge on this carbon. So we know right away that this first charge, that the first two molecules definitely have an advantage in that regard. Now let's look at the second scenario, right? Second factor. So steric repulsion. So who do you think is the winner in regards to that? This molecule right here gives the most accessibility to water molecules to access this this carbonyl carbon, right? Because they're on the right side of this carbonyl group. I'm just trying to reduce the amount of clutter there is. On the left side of this carbonyl group, there is all of this. But on the right side, there's just a simple hydrogen, right? And hydrogen is a smaller atom, and so it reduces the amount of steric repulsion as compared to these two because they are ketones, right? So adjacent on both sides of the carbon atom for both of these carbonyls are both carbon atoms. So, and since carbon atoms are larger than hydrogen atoms, and because there are bulkier groups on each side, that means that we have to realize that this is also the least steric repulsion. So we know for sure that since the molecule on the right side, since it doesn't have any inductive electron withdrawing groups, and it also has relatively higher crowding, right, or higher steric repulsion, we know for sure that these conditions don't favor shifting the equilibrium to the right compared to the other two compounds. It actually has the worst set of circumstances. So that means that it has the least amount of hydrate present at equilibrium due to the least amount of a electron deficit at the carbonyl carbon, and the most amount, a relatively higher amount of steric repulsion. Now for these two molecules, right, the chlorine atom is attached to a beta carbon, right, a carbon that's just one carbon away from this carbon. And so in terms of distance, both the chlorines are relatively the same distance away from the carbonyl carbon in both of these molecules. So that can't help us. But steric repulsion, there is a difference, right? as I had mentioned earlier, this molecule has the least amount of steric repulsion. So since it has the least amount of steric repulsion, and it also has the same inductive effects, that means that it has, it can shift equilibrium to the right the most. So that means that it has the greatest amount of hydrate present at equilibrium. So that leaves us with 2 for the first molecule on the left. So with that, we were able to rank our series. For question 5, we are given a set of compounds and we're asked to rank these in order of increasing reactivity in an SN2 process. Now, SN2 reactions, what is special about them? They are concerted reactions, or they are one-step reactions, right? So backside attack, it all occurs in one step. So because it occurs in one step, right? And if you look at the transition state, the requirement in terms of the geometry of the site that's being attacked by a nucleophile for an SN2 reaction is that there must be a, excuse me, I'm trying to say this the right way. So the carbon here must be, or the carbon that is attached to the leaving group must be a sp3 hybridized carbon atom. So the first criteria that we can use to determine whether or not an SN2 reaction is going to happen at all in the first place is to see whether that bromine is attached to a carbon that is sp3 hybridized. So here, that condition checks off, right? So it's that carbon is attached to 2 carbon atoms, to 1 bromine, and to 1 hydrogen. So there are 4 electron domains, so it checks off, sp3. And when we look at this scenario, we see that that bromine is also attached to a carbon that is sp3 hybridized. However, for this carbon, it is attached to a carbon in a benzene ring, or a benzene derivative. And that means that there are no hydrogens here. There's nothing like that. So that means there are only 3 electron domains and therefore an sp2 hybridization. And so that means that this guy is ineligible for an SN2 process. So that means that it is also the least reactive. So that basically clears one out already. Now the question is, well, we see that both of these molecules are almost identical except for the position at which their bromine is located. One bromine is just 1 carbon away from the benzene ring, so it's right here, and 1 is 2 carbons away from the benzene ring. And both of these are conjugated, right? They're both allylic bromides, so to speak. Well, they're both, excuse me, not allylic. They're both conjugated, right? They're both attached to a carbon that is attached to another carbon that has a double bond. And the same goes here. So the question is, well, where is the difference? And both of them are also secondary and secondary. So where is the difference? And this is where the concept of the benzylic position comes into play. So if for any substituent that's, especially in an SN2 process, right, if you have a leaving group that is in the benzylic position, this gives a ton more if a leaving group is in this position, right, specifically 1 carbon away from like a benzene ring, and that could also mean this position, right? There is a whole lot more resonance stabilization when you're in that position as compared to, say, this position, because when you're in allylic, right, this one is actually just an allylic bromide because it is conjugated to the bromine. Excuse me, the bromine the carbon-bromine bond is just one carbon away from the this double bond here. And so that allows it to fall under that definition. But right here, this carbon-bromine bond is a benzylic bromide, right, based on our previous definition. And for an SN2 reaction, if you're able to stabilize the transition state, right, if you're able to stabilize the transition state, the more you stabilize it, the higher the rate of the reaction. And here, it turns out that the benzylic bromide provides a higher resonance stabilization for the SN2 transition state, which in comparison to the allylic bromide. And this can be very nuanced, so you have to keep your eyes open, especially during an exam, when a compound is in the benzylic position, because resonance stabilization can play a powerful role in chemical reactivity. So since that benzylic bromide is more stable, that allows that transition state to be more favorable, energetically favorable. So that makes it the most reactive. And following that is the allylic bromide. And with that, we have finished the facts section. Now we are in part 3, the reaction section. So for this part, we are given a set of reagents and we're asked to predict the product. And this question asks us to list the product of each step as we go through. And I mean, even if it weren't the case, even if that was not mentioned, we should do that anyway, just so we can make sure that we're keeping track of how we're getting to our product. So for the first step, right, we see the following reagents. We see sodium dichromate, H2SO4, and we see it being done at 100 degrees Celsius. So we have seen this reagent before, sodium dichromate, and in Orgo 1 that might have been introduced to you as the Jones reagent, or the Jones part of the Jones oxidation reaction. So however, in the Jones oxidation, we see a noticeable a different factor, which is an important which provides an important distinction in between this and this. So that distinction is that there is water when we're considering the Jones oxidation, because that allows us to have a dilute acidic solution. However, here there is no addition of water. So that means that we have a considerably more concentrated solution of sulfuric acid, and we have it at a high temperature, 100 degrees C. So that means that there's definitely an oxidation going on, but it is way harsher. It's in way harsher settings, so harsher conditions, and that allows this to be considerably more powerful oxidant set of oxidizing conditions. And as such, if you use this set of reagents on a long alkane, on a trying to say this correctly, an acyclic alkane, or an alkane that's like this, you're capable of converting that alkane no matter how long, even if it's 50 carbons long in length. Long protein, like, whatever it might be. If it's a long alkyl chain, this set of reagents is capable of converting that into a carboxylic acid, oxidizing it actually, because it is that strong, right? In a Jones oxidation, you're able to convert primary and tertiary alcohols into a trying to say this the right way, you're capable of oxidizing primary alcohols and tertiary alcohols, and secondary you're able to convert alcohols in general, but you're not able to oxidize alkanes, because the oxidation conditions would have to be considerably stronger. So that is precisely what we get from this first reaction. Oh, sorry. Why did I do that? I meant to make this a carboxylic acid. So in the second step, we apply thionyl chloride, SOCl2, to this. Oh, and apologize. On a separate note, even though this is a very strong oxidant, it is incapable of oxidizing ethers or tert-butyl. So let me just put that as... So it is helpful in that sense, because you can selectively oxidize long alkyl chains. Now back to step 2, if you apply thionyl chloride, that will allow for you to convert the carboxylic acid into an acid chloride. So you can replace the OH group with a chlorine. So turns out that an acid chloride, as you'll find out later, is a very good intermediate between, in a synthesis, to convert two different types of compounds. So just as a heads up. But now that we've converted to an acid chloride, we have one more step to go. So in step 3, we apply this reagent. And this reagent is called the Gilman reagent. And it reacts with acid chlorides in such a way that it replaces it replaces the chlorine with whatever is inside this parentheses right here. So in that case, it will substitute in place of that, excuse me just a second, it will take the place of this chlorine right here. So when you go ahead and do that, we connect excuse me, I'm just trying to redraw the structure here. So you want to start at the carbon that is at the tail end of this parentheses, so the one that's directly attached to this metal portion of the organolithium reagent, the Gilman reagent. So, sorry, I meant to say the organometallic. So, since that is, since the parentheses, the end of that parentheses is directly connected to this copper lithium portion, we start off with a CH2 group. And then we put a phenyl group, or this group I just abbreviated as a pH just to make things simpler. So that is what we get for our final result for question 1. For question 2, we are now in a little bit of a different zone when we're considering this reaction, because now we are dealing with substituents. We're dealing with the whole game of ortho-para directors, but I'll talk about it in just a second. So the first thing we need to consider is that in step 1, we're given a mixture of nitric acid and sulfuric acid. And this combination of reagents, especially when applied to a compound with benzene rings like this, is a electrophilic aromatic substitution, or ACS reaction, known as nitration. It's a nitration reaction. So the nitration reaction will basically put an NO2 group on a benzene ring. Now, if it was an empty benzene ring, it wouldn't matter where you placed that single NO2 group. But in this case, it does. And it's even a little trickier because there are 2 benzene rings. So the first question that might be running in your head is, well, which ring does that nitration mixture react with? And it turns out that, remember, for an ACS reaction, I had mentioned earlier that the more nucleophilic you can make a ring, the more activated you can make it, the more likely that the higher the reactivity of that substrate or that reactant in the ACS reaction. So let's look at our groups here. We have a methoxy group here, and we have a nitro group here. And it turns out that a nitro group is a deactivating group. It's a electron withdrawing group. And a methoxy group is a electron donating group. And if we have an electron donating group on one ring and an electron withdrawing group on another ring, it will cause this methoxy group will inductively provide electron density to this benzene ring right here, and that will cause this ring to be activated, more activated than this ring, because this ring is losing electron density to this electron withdrawing group. This electron withdrawing group is basically sucking the electron density out of this guy right here. And what happens is that this ring becomes more activated than this ring. So since we're dealing with an ACS reaction, what that translates to is that this nitration mixture, right? What we get from this nitration, you can basically, in a way, equate this to, in solution, to a mixture of the nitronium ion, where the nitrogen is positively charged. And this nitronium ion sees that this ring is more activated, and in the ACS reaction, it will go and react with this ring. So we've got that settled. But now the question is, which site on that ring are we going to place that NO2 group? And it turns out that electron donating groups are ortho-para directors. So because they are ortho-para directors, they will want groups that are added. They will influence where the NO2 or the nitronium ion will be placed. So I'm going to label the ortho, and so this is para. These 2 guys are ortho. So the question is, where are we going to put it? Well, here is where sterics come into play. So in order for a reaction to occur to the highest yield, right? It is possible for this nitronium ion to hit any one of these three spots. But the question is asking for what? It's asking for the major product. So if we're asking for the major product, we're trying to find out the spot where the nitronium ion is most likely to bond to. So we need to find the place where there's the least amount of steric repulsion, where it's the easiest for the nitronium ion to reach. And when we look at this, we see that for the blue ortho position, it's situated right between this methoxy group and this really bulky group right here. We can treat all of that as a substituent now because this is our main focus. This ring is our main focus. So what that means is that this will be large. There will be a large steric hindrance at that point. And the question then is, okay, if the blue spot is marked out, what about the green spot? What about the para position? Well, let's compare it to the red position. And we find that both of these spots are next to a substituent. The red spot is next to a methoxy substituent, and the green spot is next to this large bulky substituent. So clearly, in order to reduce steric repulsion, it's easier for the nitronium ion to go to the red spot, right? So with that in mind, right, the major product, the most probable arrangement or the most likely spot for the nitronium ion to hit is this spot right here, because it has the least amount of steric repulsion. So if we draw that out, okay, so now we have the left ring now has a nitro group to it. And now we have another reaction. So this reaction involves fuming H2SO4. And another way to write that, another name that's given for that is, that's a name, fuming H2SO4 is the name given to the combination of H2SO4 and SO3 in a solution. And this process is referred to as sulfonation. This is also an EAS reaction. So because this is also an EAS reaction, a sulfonation reaction ends up adding a SO3H substituent to whatever aromatic ring it binds to. So because it's an EAS reaction, you want to still find the ring that is the most activated. So let's compare these two rings again. So now this time the left ring has an additional NO2 group, and since it is electron withdrawing, it will cause deactivation, but the left ring still has its electron donating group, right, the methoxy group, so that makes the left ring still more activated than the right ring. So that means that the sulfonation reaction will still occur on the left ring because it is the more activated ring. So if we go about with this process, then we need to figure out where we're going to put that SO3 group, SO3H substituent, on the left ring. So let's think about it. So when it comes to these two substituents, the methoxy group is an orthopara director, but the NO2 group, since it is a electron withdrawing group, and and it is a strong electron, excuse me, a strong inductive electron withdrawing group, that means that it's going to be a meta director. So if we look at these two, we want to find a position that it's ideal to find a position that both of these directors will lead to. And fortunately for us, that is the case. Let's first look at the orthopair director. So it turns out, well, actually, I take that back. So for the methoxy group, since it is the activating substituent, it has priority in deciding where the next substituent will be. Always keep that in mind. I apologize for that. The methoxy group, or any activating group in a ring, right? The activating group always has the last say about where to place the next substituent, because it is basically directing the course of the EAS reaction, since the EAS reaction depends on the amount of activation in the ring. So, or the intensity of the EAS reaction. So since it's an orthopair director, we see there's two possible positions, right here and right here. And since this site right here is sterically hindered, it is also unfavored. And that means that this is a no-go. So we would have to consider that the SO3H would have to hit this site. And it turns out, fortunately, that this meta director is also going to lead the SO3H to this site. But this is not the case for every reaction. So we got lucky this time. But if you have a reaction where, say, the meta director leads you to another location, but the orthopair director takes you to another direction, always, not another direction, excuse me, another site, always make sure to prioritize what the orthopair director says, because the orthopair director takes precedence in an EAS reaction. So with that settled, we can now write the final product, excuse me, as a and this would be our final answer for question 2. For question 3, we're given a benzene ring with a substituent that has a nitrile group on it, and we're given the following sequence of reactions. So the first reactant should stand out to you right away, first semester orgo, the Grignard reagent. So since we have a Grignard reagent, let's look for specifically electrophilic groups in this, and the first one that should pop out to your eye is the nitrile group here. So right away, we know that this Grignard reagent will react with this. Let me just redraw the nitrile group so it's a little easier to visualize. So when this ethyl group, this ethyl part of the Grignard reagent, basically forms a bond with this carbon, it's a carbon-carbon formation reaction, right? It causes the triple bond between carbon and nitrogen to break and turn into a double bond, because one of those electron pairs is pushed up to the nitrogen. And essentially, that causes us to form an imine salt. So this is prior to step 2. and the ethyl group is right here, these two. So now that we have, oh, almost forgot the remaining two carbons here. So you can also add the MgBr just as the positive counter ion to the negatively charged nitrogen atom. Now, the next step, as always in a Grignard reagent, is to add that aqueous workup. But what that does in this case is that it actually changes, and you'll go more over the mechanism later down the road, is that it converts this nitrogen, this carbon-nitrogen double bond into a carbon-oxygen double bond. So we get and it turns out that we have one more reagent, and this is an interesting reagent because it is part of a reaction, a well-known reaction, known as the Weydig reaction. So in this reaction, this specific reagent will form what is known as a ylide. So the resonance structure, if you're able to draw the resonance structure where this double bond, right, one electron pair in this double bond goes over to this carbon, you form something interesting. So let me just write out this resonance structure. I'm just putting the, actually no, I won't do that. Right, so this is the resonance structure for these two. I'm sorry, I know that's a little messy, but what you see here is that the carbon is negatively charged and the phosphorus atom is positively charged. And I won't go over the mechanism here, but what that does is that it will essentially allow you to convert that carbon-oxygen double bond and replace that oxygen with everything that is to the left of the double bond in the ylide reagent, or the Weydig reaction reagent. So all of this replaces the oxygen. So when we do that, when we make that replacement, we get an interesting compound. And we always, in the first atom that you replace, it's going to be a carbon-carbon formation reaction, right? And this carbon is going to be the first one that's going to be connected to the carbon on the left side of the double bond. So, I mean, if you look into the mechanism, then that's what's going to occur every time. But there is one more nuance in this reaction, which is that here, stereochemistry matters. So the Weydig reaction will result in a alkene, right? Because now we're forming a carbon-carbon double bond, but that alkene will have a trans, or, you know, if you want to use the easy notation, an E configuration, a stereochemical configuration. So when we write it out, right, I'm just going to write it as such. And now I'm going to write the left side of the Weydig reaction, of the Weydig reagent. So taking that hydrogen and that so the reason why I put it in this specific stereochemistry, right? Because if we look at the leading groups on the right side and on the left side, what is their stereochemical configuration? They're both opposite with respect to each other, right? They're across the double bond. So that gives it an E, or trans geometric isomer. It is this specific isomer, and this is an important thing to know. Okay, so trans isomer selectivity. This is what you will see for the Weydig reaction. So please keep an eye out for that. But with that, that should be our final answer for question 3. For question 4, we are given a benzene ring with a bromine substituent, and we're given 3 steps, and we're asked to find the final product. So let's go ahead and walk through these steps. So for the first step, we are given basically a reagent that has a carbonyl group, and it also has a cyclohexane on the left side and chlorine on the right side, and there's AlCl3 and aluminum chloride. It turns out that aluminum chloride is a good Lewis acid because the aluminum is electron deficient because of all these electronegative chlorine atoms, and so it causes it to be electrophilic. So it's a good Lewis acid. And it turns out that this set of reagents is actually going to be helpful in forming, and this is actually an acyl chloride specifically. And this acyl chloride and this combination of the acyl chloride and the Lewis acid will allow us to perform a Friedel-Crafts acylation reaction. So the first step with a Friedel-Crafts acylation reaction is that it will, or actually no, I won't go through the mechanism, but we're basically going to place it on this benzene. But remember, it's a monosubstituted benzene. And so this benzene has a substituent, and we want to know whether, and since this is this reaction will be influenced by the bromine group, we need to know whether or not it is a orthopara-director or it's a meta-director. And it turns out that for halogens actually are orthopara-directors. So you have, since it's an orthopara-director, you have 2 options. You have the ortho positions and the para position. So the question asks for the major product, right? And it turns out that this acyl group is bulky, it's big. And because it's a bulky group, where is it more likely to place itself to reduce steric repulsion? Right next to the bromine group or at the para position where there are no other interfering substituents? It would be at the para group, right? So if we do the first step, we end up with an acyl group. Now that chlorine is gone because these two, the acyl chloride and the Lewis acid, interact in such a way that, as you'll see in the mechanism, you end up basically attaching this guy to the benzene ring. Now, I'm just gonna abbreviate it to make it my life a little easier. So I'll just abbreviate this cyclohexane ring as CY. That is an abbreviation that is used for cyclohexane rings. Now, because we have this benzene ring with two substituents that are paired with respect to each other. And in the second step, we're given a methoxy salt, sodium methoxide, and we are going to expose that to our current material, our current intermediate, to that sample at 100 degrees C. So step 2. And it turns out that the methoxy anion is a very good base because methanol is not such a great conjugate acid, right? The strength of the base is also inversely proportional to the strength of the conjugate acid. So it's a strong base / nucleophile. So because it is a strong nucleophile, we want to see if it can basically undergo a NAS, or a nucleophilic aromatic substitution reaction. So let's talk about that for a second. So a NAS reaction has two possible pathways. The first one is referred to as the addition-elimination route. Now this is preferred because when you have a nucleophile and it's at 100 degrees C, it's typically around mild conditions, and because the second path, elimination addition, is considerably harsher, right? We want to go down the path that requires the least amount of extreme conditions. For the second pathway, we would need really high temperatures, around 340 degrees C, and pressures that are about 2,500 psi. So very intense, harsh conditions. And it even involves the formation of a benzene intermediate. So basically, a benzene ring, but with with a triple bond at one point, which is incredible because, I mean, if you were to be really technical about it, it would be kind of like a quasi pseudo triple bond, because there's the second p orbital that's involved in the overlap is quite weak, so it is a weak triple bond, but it is still a triple bond, so it is a very strange intermediate, and it works with specific bases such as sodium amide and potassium amide and certain metals as well. But for us, for our purposes, we're doing the first pathway, addition-elimination, and that is also the case since we're dealing with low temperatures, relatively lower temperatures, such as at 100 degrees C, compared to the second route. So if we do a nucleophilic attack, right, what is a good leaving group here? A good leaving group in this second state. Turns out it's the bromine, right? We've seen that for SN2 reactions and so on. So turns out that you can do a nucleophilic substitution. I won't do the mechanism here, but you will end up getting a methoxy group in lieu of the bromine group. Now we have one more step, and this step involves a interesting mixture of reagents. We have a sodium metal in ammonia liquid and in methanol solution. So this set of reagents is part of a reaction that is known as the Birch Reduction. Now, what the Birch Reduction will do is that it will basically in short, and this is a very vague description of it, but you'll basically go from a benzene ring to a ring that only has two double bonds, but there are more specifics to it. So a Birch reduction can be greatly affected by electron withdrawing groups. So if we look at our current product, we see there is a methoxy group and this acyl group, and it turns out that the acyl group is a very good electron withdrawing group. And the Birch reduction will cause the, it will cause basically one of the, I'm trying to say this the right way. If there was so reduction, right? The word reduction, it can mean the removal of bonds to, it can mean, the removal of bonds to oxygen or adding hydrogen bonds. So in a Birch reduction, if there are strong electron withdrawing groups, it will cause a reduction at the carbon that is attached to the electron withdrawing group by adding hydrogens, and it will also cause a reduction at the carbon that is para to the carbon that is attached to the electron withdrawing group. So I'll show you what, I'll write out the structure just so it makes a little bit more sense. I won't, again, show the mechanism, but basically you have your acyl group, but originally, look what happened here. In this case, there was no hydrogens here, right? There were no H's here. There were no H's here, right? But in the Birch reduction, because this is a strong electron withdrawing group, there will be a hydrogen added here. And that is a reduction. And this will also ultimately cause there to be, before I do that actually. There will also be a reduction at the carbon that is ortho to this carbon. And the carbon that is ortho to this carbon is this carbon, right? So there will be a reduction at that spot too. So at the carbon of the methoxy group. So now we have we've reduced those two sites. But in addition, we've also put the two, now instead of having three conjugated double bonds, we have just two that are aligned in the direction of the electron withdrawing group. So the way that we've put it so far is in a Birch reduction, for the two carbons that are reduced, right, the ones that are ortho to each other, situated in between them, you'll have just two double bonds like this. If you look into the mechanism, you'll be able to understand why it gets to this particular arrangement, but I won't be going over that. For the sake of time. So for question 5, we have this thioacetal, and we're asked what reagents will allow us to get to this product right here. Now, the first thing we need to understand is that a thioacetal is a good intermediate in a lot of reactions. It's a good midpoint, so to speak, because once you have a thioacetal, you can be reduced to a carbonyl group, such as this, and basically what happens is that what we're trying to aim for is we want to basically construct a backbone for the rest of this structure around this thioacetal, and then convert this thioacetal into a carbonyl group. So what that would mean is that we have to first, let's try to make this thioacetal suitable for putting the other pieces together. So when I mean the other pieces, I'm referring to all of this, right? There's already a hydrogen here. There's two hydrogens here, but let's try to replace this hydrogen with this group right here, right? So if we go ahead and do that, right, the first thing we would have to do is we would have to remove that hydrogen. But since it's a carbon-hydrogen bond, it's kind of difficult to remove. So the first thing we would need to do is we would have to utilize a strong base. And one of the strongest bases that you'll see in ArgoChem is N-butyllithium. This reagent is a very strong, very strong base. It has a pKa of around 50. So way stronger than, typical like sodium hydroxide or things of that nature. So it's strong enough to remove a hydrogen, a hydrogen from a carbon. So if we apply that first step, right, we remove that hydrogen. We are left with this lone pair. And when that happens, right, and also this is a carbanion. Now we have a nucleophile. So I'm pretty sure you can see where I'm going with this, because if you have a nucleophile and you want to have this fragment added to the thioacetal, right? So we can have a nucleophilic substitution reaction that will do this for us. And it turns out you can do a SN2 reaction, actually, to get to this point. So you can use a alcohol that basically allows you to connect everything to the right, or this circled portion, to that thioacetal. So let me just draw it entirely. Right, so I'm just redrawing the entire right section, but I put this alkyl halide right because once I replace this alkyl halide, it'll be with that thioacetal, we're one step closer to getting to our desired goal, right? So if we use that second reagent, right, an SN2 reaction, although it will be bulky, it will cause ultimately a reaction in which we get this intermediate. And now we're very close to the end, right? Now, like I had mentioned earlier, now we're at the stage where this is merely just a placeholder for what we want, right? It's the carbonyl group. So how do we convert this thioacetal into a carbonyl group? Well, it turns out we can use a specific set of reagents to convert it, and that conversion process is known as hydrolysis. So the hydrolysis of this thioacetal can be done via using mercury chloride in acidic solution. And that will allow us to get to our final solution. So this is how we put the pieces together to get to our final point. But the key thing to understand when we were solving this problem was that we had to understand what the role of this thioacetal group was. And typically, remember, just keep in mind that thioacetals are typically used as starting points, as building blocks for making a molecule, and you can then replace that thioacetal with a carbonyl group. So just keep that in mind. And for the last problem in the reaction section, we have a benzene group and an aldehyde substituent. And we have two reactions that we have to do in order to get to the final product. So the first one is a very familiar one. So we have bromine and iron bromide. So this is actually a bromination reaction, and turns out that this is an EAS reaction, right? And so again, with EAS reactions, they are going to be affected by ortho, para, and meta directors. So let's try to evaluate what type of director this substituent is, because that will affect where we place our bromine substituent. So this aldehyde group, the carbon, because it is doubly bonded to an oxygen that is more electronegative than it, it will have a partial positive charge. This electron deficit will cause it to become an inductive electron withdrawing group. Since it is an inductive electron withdrawing group, and it's a relatively strong inductive electron withdrawing group, it will become a meta director. And if it is a meta director, then we know two spots where it could potentially land. It could land at either of these two spots. Now that we have that first step down, let me just write down. So this does not result in polybromination, right? So we will only have one, it will only land in one place, but because of symmetry, it doesn't matter where we put it in. It won't have a chemical difference, the final product. So because of that, now I'm just going to choose the one at the bottom. And for the second reaction, we have sodium nitrile salt in acidic solution. And the question is, well, what is this nitrile group going to do? Right? Because we know that the sodium ion is a spectator. So we see that, again, like I mentioned earlier, there's a partial positive charge on this carbon and a partial negative charge. So that makes this carbon electrophilic. And this is a nucleophile. So it's going to be an addition. Because let me just write it out in a little bit more apparent way. Right, so this lone pair is going to go and see this partial positive charge, and it's going to go attack it. And when it forms that bond with, that carbon forms that bond with this carbonyl carbon, it causes this lone pair on the carbon-oxygen double bond to migrate upwards to the oxygen, and we are left with a salt. So let's see what we get. So because the charge went up to the oxygen, it has a negative formal charge, but that's where the spectator, sodium ion, comes in, right, to stabilize the charge. And now we have one more step, which is a reductive workup. A reductive workup. So that's where the H plus comes in, and it basically protonates that oxygen, and we are left with Sorry, my pen is acting up again. And that would be our final answer for question 6. And with that, we're finished with the reactions portion. We are now at part D, and we're asked to provide a mechanism for this reaction. So what we find here is in the instructions it says that to draw all the intermediates and to show all the formal charges. And when we go about doing this process, the first thing we need to do actually before we even dive into the mechanism is to understand the actions that are being done to go from point A to point B. So when we look at the product and the initial reagent, what are the commonalities we see? So we see that there is this benzene group that is attached to a hydroxy group. And what are the differences? We see this acyclic substituent that is also attached to the benzene ring on the reagent, but in the product we see a ring. So, and even within these differences, we can still spot a little bit more, a few more commonalities. We see that in the ring, there is a carbon that has 2 methyl groups attached to it, and in the chain, we see that there is a carbon that is attached to multiple methyl groups. So we're seeing that we're not adding any, there's no carbon-carbon, actually, what I'm trying to say here is there are no outside reagents that are bringing in new carbons of any sort or anything. So the task that we have to face, is we have to determine what actions have to be done in order to convert this long chain into a ring. So one task is ring formation. And another difference that we spot is that there's an OH group here, right? So we see that that OH group is not there in the product, so removing the OH group. And another weird thing is that we see that one carbon is attached to 3 methyl groups in the reagent, and the other corresponding carbon in the product has 2 methyl groups. So there is some sort of movement of groups. So perhaps a movement of methyl groups, perhaps a methyl shift. So see what I'm doing here. I am basically going through the examining, really comparing the product and the reagent, and I'm trying to piece together what has to be done throughout the mechanism before I even do the mechanism. So it's like brainstorming what your strategy is going to be, how you're going to structure out the mechanism, what's your proposed mechanism for this. So these are really the 3 main things that we had to look out for. So when we look at our reagent that's used, it's HCl. And HCl, as you already know, is a strong acid. And HCl, if it sees an OH group as an acid, what is it going to do? It's going to try, there's going to be a acid-base reaction basically at that OH group. And what's going to occur is that there is going to be the formation of a positively charged water substituent. And as you know already from previous tests and from previous questions, this group is a very good leaving group because once it relieves, it forms water molecules, which are incredibly stable. So this is indeed a good leaving group. And the question you might be asking is, well, why didn't I try protonating the OH in the next to the the benzene ring? So the reason why why the OH here can't really engage in an acid-base reaction with the HCl is because it's part of this. The OH group actually serves as a resonance EDG, or resonance electron donating group. So what that does is that the electrons are actually engaged in the conjugated pi structure, and what this does is that it makes it less susceptible to produce the major product actually. So, and in addition, just on a more practical note, we have the same group here, right? We don't want that to be touched. In reality, there is a chance it may interact, but it's unlikely because there is also a chance that could interfere with the resonance of the ring. Because if you're able to protonate the water group, and if it leaves, then there's a chance that the creation of a carbocation on that benzene ring could affect the stability of the structure, so that might be energetically unfavorable. But for our purposes, since if you don't want to go down that conceptual loophole, if you see this benzene ring with the OH group, and they're common in both the reagent and in the product, then you can treat that as a fixed thing. You don't have to deal with that. So in the next step, we see that since I had said earlier that the water is a good leaving group, it will depart from the molecule, and we're left with a secondary carbocation. Now this secondary carbocation is indeed susceptible to rearrangement, and this ties in back to our previous prediction, right, about the possibility of a methyl shift. And there is good grounds for having a methyl shift as well, because if you move this methyl group over here, what you're going to get via methyl shift is a tertiary carbocation, right? Because this was a secondary carbocation. This is a tertiary carbocation. So it's definitely a more stable carbocation. That's why this methyl shift would occur, right? It's to produce a more energetically stable carbocation. So this actually aligns with we're getting closer to the product because we see that there is a carbon that's attached to two methyl groups here, and a carbon that's attached to one methyl group, and voila, what do we see here? We see a carbon that is attached to two methyl groups and a carbon that is attached to one methyl group. So we're getting closer, and we see there's a plus. Since there's a carbocation, we know there is a chance for basically a elimination reaction where we, excuse me, not elimination, an addition reaction where basically we, that was not expected. So we can cause a pair of electrons to migrate out and interact with this pair of this carbocation, and we get one step closer to the final product by creating a ring. So since that electron goes out, excuse me, sorry, that was a small error on my part. So now we are very close to forming the ring we want, but we have a carbocation, actually not at that carbon, at this carbon, because this carbon corresponds to this carbon right here. By losing that double bond, we form a carbocation there. Now, the very last step is to perform an elimination. So the first step we had done was to do an addition by breaking the double bond in the benzene molecule, but now we are going to restore that via elimination, because there is a hydrogen atom at this carbon, and what that's going to do is, what's going to happen to it actually, is that if we have an anion, say the chlorine anion from the first step that was formed whenever the acid interacted with the OH site on the substituent, that chlorine is going to go and interact with that H, and that's going to cause the electrons between the CH bond to migrate back to the bond right here, ultimately forming our final product as the final answer. And with that, we are able to show that the first and the second predictions were also true. So the point I'm trying to get at through this is whenever you go about doing a mechanism, even, make sure that you really study the reactant and the product, and you try to see what are their commonalities, where are they different, because that will tell you hints about what you have to do along the way. And with that, we have solved the mechanism. Now we are in part E, the synthesis portion of this exam, and we are given the following molecule, and we're asked to synthesize it from benzene, alcohols of 3 carbons or less, any inorganic reagents, and any oxidizing or reducing agents. So we have our set of starting materials already defined. So our task is basically to break this molecule down all the way to its starting points via retrosynthesis. So let's go ahead and look at the different groups on this molecule so we can get a better idea of what's going on. So we see here that there is an alkene chain down the middle, and attach this alkene chain on both ends of the double carbon double bond. We see there are 2 phenyl groups that have a nitro group attached to them. So we note this, and we note that on each of these phenyl groups we see there's a nitro group that is actually in the para configuration with respect to the alkenes. So they're on the other side of each of these rings. So that already gives us a clue about the order of the reaction sequence. And let's note a few details about NO2 here. So we see that the NO2 substituent, it's a electron withdrawing group, right? It's a very strong electron withdrawing group. And if you were to actually draw out the formal charges on that substituent, you would see there's a full-on positive charge at the nitrogen. And so it makes it a very sensitive material when it comes to using rather reactive reagents like the Grignard reagent. So let's note that down. So there's no Grignard presence of NO2, and that means that we can't do any carbon-carbon formation reactions, or any, at least with the Grignard reaction. We can't use the Grignard reaction for this while we have this group. And another thing that we have to note is that the NO2 reaction is, the NO2 substituent is also a meta-director, right? So if we had the NO2 group here first before the alkene group, it would not make sense because the NO2 group could not direct the alkene group to a para position, right? Even though that's what we see here. But we do note something else. We see that the alkene group is actually a orthopara director, and so it makes sense that the alkene would be attached to the ring even before the NO2 group was added, because then the alkene could direct the NO2 group to the para position. And I am aware that since it is the orthopara, it's an orthopara director, there is a chance it could also go to the para product, the ortho product. So I know there is that possibility, but since this is the molecule that we were asked to do a retrosynthesis on, we could assume that this molecule can be isolated. So let's say that this is the isolated para product, right? So that means that if we go back retrosynthetically, we can consider a molecule where there is no NO2 group. So we go back one step and we've removed those retrosynthetically, and we remove those NO2 groups. And the question is, well, how do we go from this point to this point? And that should be rather straightforward because in the previous reactions that we've covered, there's a very specific EAS reaction that allows us to form NO2 substituents on benzene rings, and that is the nitration reaction, and it involves the reagents HNO3, H2SO4, and if you want to be more specific, we could also include the fact that there are two equivalents of it, so we can form the two substituents here, right? Just as an extra specification. Now we are at this step, and we want to break this down even further because we haven't gotten down to any of our desired starting materials yet. So the question is, how do we cleave this at this point, right? So one way that we could go about doing this is that we could basically perform an elimination retrosynthetically. We could convert this double bond into a single bond, and this would be totally fine because none of the starting materials are alkenes that we need to worry about. So we could convert this double bond into a single bond, and let's consider the case where that is a single bond. So you might be wondering why I added the OH and the H groups here, right? Because I was setting this up for an elimination, right? If we do an elimination, and specifically an E1 elimination, we can remove this OH group and also remove this H group and allow for the formation of a double bond here. So what reagent would allow us to do that? We can use a strong acid such as H2SO4 and heat to favor the elimination reaction. And this would be an E1 elimination. Right, so we're just thinking about forming a alkene, but we think about it in the reverse direction, so we can go back one step retrosynthetically. Now we've got to this point, and the question is, well, how do we go to a benzene or to any of these alcohols or anything? Well, one way is we can still continue to work on this specific location, and if you notice, we can actually do a Grignard reaction if our aim is to break it down, because we don't want these two benzene groups to be together, right? We want them to be split, and so we can eventually isolate them. And one way we can isolate them is we can split this carbon-carbon bond by considering a carbon-carbon formation reaction, so the Grignard reaction. That was my rationale for doing that. So if we break this down into Grignard reagents, this would actually be in this form. So look what I've done here. I have basically I made this side of the molecule the carbonyl containing group, and I've made this group the Grignard reagent, right? So just as a side note, the pH, again, like I've shown earlier, the pH abbreviation is just used to refer to the phenyl group, and the ET is referred to the ethyl group right here. Just wanted to make that clear. And the next step would be, well, now we have two materials we're working with. Well, which pathway do we go down? So let's first just choose the Grignard reagent, right? This reagent right here. So whenever we make a Grignard reagent, right, let's go back one step before we added the magnesium, and we have the following alkyl halide. So we see right here that the reagent we could use for this is magnesium metal and ether. So now the next thing is, well, how do we go in further? Because we're not allowed to have alkyl halides in our starting material, right? So we would have to consider what group can we add here? What group can we what is the easiest group to form here? Be this bromine, right? And especially because, let's consider the position of this bromine, right? We have a benzene ring right here, and we have a carbon that's directly attached to that benzene ring. So do you remember what that position is called? If a substituent is on a carbon that is directly attached to a phenyl ring or to a benzene ring, what would that be? That would be the benzylic position, right? And this benzylic position especially favors, it basically is a hotspot for reactions such as halogenation. And that means that if we do retrosynthetically a halogenation reaction, we can get from this point to this point with a high yield, right? We won't have bromine groups popping up here or anything like that. There will only be a bromine group added here, right? Because of the very fact that it's in a very special position, the benzylic position. So there's two ways you can go about doing this for our bromination reactions, right, orgo-1. So we can use N-bromosuccinimide or NBS with light, or we can use bromine with light. It's either up to you. So now we've got to this point, and the question we need to ask is, oh, I forgot one thing. My bad. So now the question we need to ask is, okay, how do we go back even further, right? How do we, because we're not at an isolated benzene ring yet. But the other question is, well, how do we deal with this big propyl group that's attached to the benzene ring? And one way we can go about doing this is, let's say we had the scenario where this carbon is, so basically we have to think backwards in terms of a carbon-carbon formation reaction, right? Because if we want to sever this bond, right, we want to isolate this guy, then we need to think of a formation reaction. And one way we could do is kind of like a reverse reverse Friedel-Crafts acylation, right? So a Friedel-Crafts acylation would allow us to, a Friedel-Crafts acylation would allow us to add an acyl group to this phenyl group, and that would allow for there to be, and once you convert that carbonyl on the acyl group to a, once you reduce it down to a CH2 group via a reduction reaction, that will basically give you a propyl group, right? So let me explain what I'm trying to say here, because I don't want to confuse anyone. So let's go back one step, and let's say that we could retrosynthetically oxidize this carbon and have a CO double bond here and the CH2, the ethyl group here. I feel like, let me make it a little bit cleaner. So this looks very familiar. Turns out that this is the same as this, right? So if we can go backwards and do a retrosynthesis on this, then we're also working on this molecule. So that's pretty neat. So like I had mentioned earlier, we have this phenyl group here, and now we have this acyl group here as well. And if we do a Friedel-Crafts reaction, we can go from this point, let me draw the molecule first. So now I'm going to draw it out in its full form, the pH, as this ring, right? So now we have a Friedel-Crafts acylation. So we basically created an acyl group, an acyl chloride, right, with the same group here, but now I've just tacked on this chlorine, right, to make it a suitable reagent for the Friedel-Crafts acylation. And one important ingredient in this reaction, so to speak, is using a Lewis acid catalyst. And since we're having chlorine here, one suitable reagent for this acylation reaction, this Friedel-Crafts acylation reaction, is the Lewis acid AlCl3. So we've gone back one more step, and now we're getting near the end. We've successfully isolated the benzene, right? Now the question is, well, how do we break this down even further? So it turns out we can actually go backwards and change this into an alcohol, right? So one way is we can convert this acyl chloride into a carboxylic acid group, and that would be done using the CH2, CH3, COOH. Now we're at the acid, so we're very close to an alcohol, right? All we need is to continue the oxidation, or excuse me, the reverse oxidation. So we're thinking about this in terms of reduction now, because we're going backwards. We're thinking about it in terms of reduction. So now let's say that if we were to convert this all to an alcohol, right? What alcohol would we have? We would have propanol, because all of this would be removed and we would just have two hydrogen groups, two hydrogen atoms that are attached to this carbon right here. So how would we go from, I do not mean to add that OH2 there. Okay. So how would we go from propanol to this acid right here? So that can be done through a simple, going back to Orgo 1, a Jones oxidation, right? Jones oxidation reaction, or using the reagents sodium dichromate in acid in water. Either way. So now we have successfully gone down all the way to a alcohol of 3 carbons, right? So that checks off that requirement right there. So we've isolated backwards, and guess what? Since we had to retrosynthetically go back all the way for this particular product, and that product is the same as this product, this is already synthesized at this point, right? We've already synthesized this material once we made this guy right here, because they're both the same. So we've pretty much finished our synthesis, and the takeaway here is, especially when it comes to dealing with molecules that have aromatic rings, try to use the relationships that you see, such as the orthopara relationships. If you see a substituent that's a particular type of director, try to piece together, well, how would we order the addition of each of these substituents to the ring in such a way that we respect the fact that, they're either orthopara directors or meta directors, right? So we knew that in this case the NO2 group was a meta director, so we knew that that couldn't have been the first thing attached to the ring. In fact, we knew, and from that we realized that the alkene group, which is an orthopara director, would have probably guided the formation of the NO2 groups in the para position, right? So it's important to realize that for these types of problems, you are given kind of an implicit hint about about the ordering of these groups relative to, like on a aromatic ring, by knowing, if you're able to understand the properties of each of these groups, right? So make sure that you understand what each substituent, common substituent like NO2, SO3H, whether they're orthopair directors or so on and so forth. So if you're able to keep that in mind, that's a huge upper hand that you have, especially in a retrosynthesis like this. And with that, we have finished this problem. Now we have reached the last portion of the exam, the spectroscopy section. And we are given a compound with the formula C11H14O. And we're given an IR spectra, NMR spectra, Proton Nmr spectra, and a carbon-13 NMR spectra. And we're asked to determine the structure of the compound using the data that we have been given. So first things first, when it comes to these problems, one of the first things you want to do is to calculate the degrees of unsaturation, because that will tell you the total number of double bonds and rings that will be in the structure that you're trying to construct. So it's a good checking point. So let's go ahead and start with that calculation. So the formula for the degrees of unsaturation is 2C, so 2 times the number of carbons in the molecule, plus 2, plus the number of nitrogens of any, and minus the number of hydrogens, and also minus the number of halogens, all over 2. So if we look at our formula, C11H14O, and if we plug in the numbers, we should be getting, right, there's 0 nitrogens, there's 14 hydrogens, and there's 0 halogens. We get 5. So again, this is the total number of double bonds and rings. And this unsaturation number also tells us something else. It tells us that there is a possibility of having a benzene ring, right? Because benzene's molecular formula, C6H6, has a unsaturation number of 4. So since we have 5, that means that 4 out of those 5 degrees of unsaturation could come from a benzene ring. So it's a good hint to keep in mind. So let's dive right in and let's look at the IR spectra first. So just to make my life a little easier, I'm going to block out the fingerprint region. So you can say that's around 1500 wave numbers. So let me just gonna block it out so we don't have to focus on that. And let's just keep our focus on everything past the 1500 wave number. So we see some noticeable peaks, and let's try to figure out what they are. So around 1600, so 1597.26, we see a moderate peak, and it turns out that this is for a benzene group. So that matches our previous guess, right? So there definitely has to be a benzene group. And around let me get the number straight, around, I think it's 1687.95 wave numbers, we have a very sharp peak. And this peak typically corresponds to a carbonyl group, CO double bond. And that is also good because in our formula we see there's one oxygen atom, so we know that that oxygen atom could be attributed to a carbonyl group. So that is also a helpful observation. Now let's look around the 300 region. So we don't see any large grooves here or anything corresponding to an alcohol or to a hydroxy group. We don't see any sharp peaks around here, so we know there is also, we don't have to worry about having aldehydes of any sort. But when we look at right next to the 3000 region, we see peaks that are very close to the 3000, but just lower in wave number. And it turns out that this region corresponds to sp3 hybridized carbons that are attached to protons that are associated with sp3 hybridized carbons. Sorry, that's what I meant to say. So the NMR has given us some pretty good information, and if this is sp3 hybridized, then we know there has to be some carbon-hydrogen bonding outside of the benzene ring. So that gives us an important clue as well. So now let's look at the Proton Nmr. We see in the Proton Nmr that, let's go from upfield to downfield. So we see right off the bat, we see a group of peaks in this 0 to 5 chemical shift region. Sorry, 0 to 2.0, 0.5 to 2.0 ppm chemical shift region. And we know that these have to be related to the proton signal that comes from the for a CH single bond, right? So when we look at the splitting patterns, right, if we look at the splitting pattern of this set of peaks, we see there are 3 distinct peaks. And this tells us something, right? Remember the n+1 rule? So by the n+1 rule, since there are 3 peaks, it's a triplet, that means that there are 2 neighboring carbons here at this point that are next to the carbon that is attached to our proton that is corresponding to this set of peaks. So the right way to say this, the right technical term, is 2 neighboring, not carbons, I apologize, 2 neighboring protons that are chemically equivalent. So that's an important clue. It tells us that there is the likelihood of having a carbon chain that is outside of the benzene ring. And the reason why I say the benzene ring, outside the benzene ring, is because remember from the IR spectra, we had seen that there were sp3 bonds, sp3CH bonds, which you do not see in a benzene ring. So that definitely tells us there is an alkyl chain outside of the ring. So by the integration number, it's 3 hydrogens, so we can say this refers to a CH3 group. And if it's a CH3 group, it's probably the end of this alkyl chain that we're guessing there exists. So the next thing is we see these very splitted set of peaks here, and we see that the integration number for each of these is 2. So that means that we have CH2 groups here. And let's see if their splitting makes sense. So right here on the one to the right, we have a splitting of about 4, or actually no, probably 4 to 5, and around the same for this peak as well. So this makes sense because this probably means, for this one at least, that this one is situated in between these 2 groups, right? And that means there's a likelihood of there being a chain from this guy to this guy. And the question is, well, where does the splitting for this come, right? Because we see there's a lot of peaks here, and it can't just come from having a neighboring CH2 group. So turns out that we need to also consider what is to the left of this alkyl chain. And when we look at and when we go further downfield, we see there is a very clear and pretty intense set of peaks around the 3 ppm region, corresponding to 2 protons. So turns out that this pair of electrons must be next to some very influencing group that causes it to be shifted down considerably downfield relative to the other CH2 and CH3 groups. And before we go into that, right, let's just say that this would also be a CH2 group because it is still relatively upfield, but we know that something is nearby which is causing this CH2 group to be affected considerably. So it turns out that when we look at let's look further downfield and into the 7 ppm to 8.5 ppm region. And this one should immediately strike you as a different set of protons. And because it's so far downfield, we know that this has to be attributed to the aromatic protons. Aromatic. And we see from the integration numbers that there has to be 5 CH bonds within this aromatic ring. So that means that the ring is monosubstituted. One carbon in that benzene ring is not bonded to a hydrogen. And that absence of that one hydrogen gives us a total number of 5 aromatic protons. So in that case, right, let's just draw the structure. So we have 5 protons, as the integration number tells us. And now the question is, well, what is this guy right here? So we had suggested earlier that there has to be some sort of alkyl chain outside of the benzene ring, right? So we know there is a possibility that all of these groups may be stringed together to form a larger alkyl chain that would then be connected here. But that's not the only piece in the puzzle, right? Because from the chemical formula, we see there's an oxygen here. So something seems a little off. So one way we can go about doing this is we can just do simple counting of the carbons and the hydrogens. So let's see, we have from the benzene ring, we have 5 carbons, and if we include the number of carbons from the chain, right, we have 1 here, 3 here. So 1 plus 3 is 4, plus 5 is 9. So we have, we are referring to carbons, I apologize. So I accidentally mixed it up for a second, not the hydrogens. The carbons, we have 6 carbons, and that means that we have, in total, so far, we have 10 carbons. And they're asking for 11 carbons. So that means we're missing 1 carbon, right? And now let's consider let me just write this down to be more clear. So we had 6 from the aromatic, we had 1 from the CH2 group, and we had 3 from the other 3 that were close to each other in the 0.5 to 2 ppm region. So far we have 10, but we are missing 1. So that means there's 1 missing. And in the hydrogens, we have, from the aromatic ring, we have 5. And from all the CH groups, we have we have in total, if we count it, we have 4 plus 2 is 6 plus 3 is 9. And that gives us 14. So we have all the hydrogens we need, but we're missing a carbon, and we are missing one oxygen. If we're able to get one more carbon and one more oxygen, then we'll be able to basically make sure that we have all the atoms for our desired structure. And voila, one thing that we see is that there's a group that is having one carbon and one oxygen. It's that CO double bond. So we know that that CO double bond has to be situated in this overall molecule. So it's a confirmation of what we see in the IR. And since this group of peaks has been significantly shifted downfield, this corresponds actually to the proton NMR signal you get for a beta proton that is attached to a carbon, which is attached to a carbon of a carbonyl group. So that means that there is a carbonyl group that is directly bonded to this CH2 group, and that accounts for the fact why this set of peaks is significantly shifted downfield. And in addition, we know that this must also be connected to the previous chain of CH2. So now it makes sense. So if we were to connect this all the way to this group, this carbon to that carbon, the carbonyl carbon, then we have ourselves a complete structure that respects the observations that we see in the Proton NMR and in the IR. So what that means is that we've basically knitted together our entire structure, and it turns out we don't really need the proton and the carbon-13 NMR, but just to be sure, we can also go through that. So in the Proton Nmr, from the range of 10 to 50 ppm, we have these peaks correspond to alkyl groups. So they could be, but this is still somewhat confusing because there's lots of overlap between primary, secondary, and tertiary alkyl groups. But generally, as the degree of substitution goes up, the peaks are shifted more downfield. But it does tell us that yes, there are alkyl groups out here. And this is specifically alkyl groups that are not within an aromatic system. So it does confirm the fact that there is this chain right here, or that there are CH2 groups that are outside of this benzene system. So now that we have that part settled, let's look around the 120 to 140 ppm region, and we see this set of peaks, one with having the strongest intensity, and there's one that's very small. And so what this tells us, especially since it's around the 120 to 140 ppm region, is that these three peaks correspond to three different types of carbon atoms in the benzene ring. And this makes sense because if we look at our previous model for the ring, what do we see? So I'm going to highlight these groups. So we see that there are two protons that are adjacent to this whole chain, right? This long chain right here. And we see that by symmetry, everything on the right side should be symmetrical to everything on the left side. So this pair of protons, are the closest to this long carbonyl chain, and we see that they must therefore be chemically equivalent. But if you go down one set of carbons, you get to these guys, and these are the same distance away from the long chain, but the thing is that they're not as close to the long chain as excuse me, I do not mean to highlight the protons here. I meant to highlight the atoms themselves, the carbon atoms, because that's actually what's being recorded by the carbon-13 NMR. My apologies for that. So we have this different set of carbon atoms that are chemically different, right, based on their distance from the long chain. And this makes sense because it comes, it's in agreement with our carbon-13 spectra, and it means that there are indeed three different sets of chemically different carbon atoms, right? We have one, two, three different groups, right? So that comes into agreement with our IR spectra, with our previous model for the aromatic ring. So that is good, and that means that we have one more thing in the carbon-13 spectra to note. We also see that there is this little peak up here, and this actually corresponds to a ketone. And that is also in agreement with what we said. This is an additional reason for why we have this, why I decided to link the carbonyl group with the ring and also with the chain of CH2CH3 groups, okay? So that's the additional reason for why we linked it, because it matches our carbon-13 NMR. So now that we have all of that settled, we have finally been able to confirm and verify that this is the structure for our molecule, which I'm drawing out right now. So if we, just to double check, if we count our carbons, we have 6, 7, 8, 9, 10, 11. We have 11 carbons. And if we count the hydrogens, we have 5 from benzene. We have 9 from this carbon chain, so that gives us 14 hydrogens. And we have 1 oxygen in our carbonyl group. So that means our formula is correct. It matches with the previously given formula. And if we check the degrees of unsaturation, right, there are 4 degrees of unsaturation corresponding to this ring, and there's 1 degree of unsaturation corresponding to the CO double bond. So with that, we should be all good in terms of the unsaturation number, and we have successfully found out the chemical formula. And now we have finished the first portion of our review. We've completed our review of the exam, and now I will be going over the multiple choice questions. Now we are in the multiple choice section part of this review, and let's dive right in. So for question 1, we are given a set of structures, and we're asked to determine which of these structures is aromatic, assuming all of these are planar. So this is very similar to the previous question that we saw in the facts section of the previous portion of this review. And that means that we know what to do. We can apply Huckel's rules in order to determine the aromaticity of these compounds. So let's start off with choice A. So let's apply Huckel's rules in determining whether or not this structure is aromatic, non-aromatic, or anti-aromatic. So for the first structure, we see that it is cyclic. We're allowed to assume that it's planar, and all of the carbon atoms on this are sp2 hybridized. So that means that all of these do form a conjugated pi ring system. And we also see that there are 8 pi electrons. And since 8 is a multiple of 4, the 4n rule applies. So 4n rule applies. So that means that we have a anti-aromatic structure for A. So A cannot be the right answer. For B, we have a cyclic structure. It is planar, and all of the groups are conjugated because all the atoms are sp2 hybridized. And when we count the number of electrons, we get 16 pi electrons. And again, since 16 is a multiple of 4, the 4n rule applies. So we have anti-aromatic, so B cannot be an option either. For C, we see that we have a cyclic planar compound. Again, for the same reasons, it is conjugated. All the atoms are sp2 hybridized, and there are 12 pi electrons. So again, the 4n rule applies. So we still have anti-aromatic. For choice D, even though we can select D by elimination just to be sure, right? That's what you have to always do for these problems. Just make sure that the answer checks off conceptually. We see that all of the atoms are conjugated because they're all sp2 hybridized. And when we count the number of pi electrons, what do we get? We get 18 pi electrons. So 18 pi electrons is not a multiple of 4, but if you think about it, you can get 18 by doing 4 times 4 plus 2. So the 4n plus 2 rule applies. So therefore, D is aromatic. That is our final answer for question 1. For question 2, we are given the following set of structures, and we are asked to determine which of these structures have 8 pi electrons. So this also ties back to our discussion of aromaticity, but the reason why I included this question is because even if it seems simple, it is often a tripping point for a lot of students, just because sometimes you include electrons that are not intended to be, you include some electrons into the pi ring system that are not intended to be pi electrons. And that can mess up your evaluation of whether that structure is aromatic, anti-aromatic, or non-aromatic. So it's important to make sure you really know how to count the number of pi electrons, because sometimes there are tricky cases that we've seen before. There are heteroatoms that might require you to evaluate multiple cases and then choose the lower energy, more stable case, right? So it's not as simple as merely just counting the number of electrons that are in the overall structure. So it's you have to apply some judgment sometimes. So let's go through our choices and see what we have. So for part 1, we can count the electrons on the pi bonds, on the double bonds. So we have 4 so far, and at the there are 2 heteroatoms, the 2 nitrogen atoms, and the question is, can we include this pair, these 2, as pi electrons? And it turns out that whenever you have a heteroatom X, so for a heteroatom X, it's just arbitrary. We have heteroatom X, we have H, and this is the rest of the molecule. And there's a lone pair. This lone pair will be involved in pi bonding with the rest of the conjugated system, while this hydrogen will be perpendicular with respect to that lone pair, just as an additional note. So really this this heteroatom would have an sp2 hybridization, because you wouldn't really count that lone pair as a part of, it's not a localized lone pair, right? So only localized lone pairs can be accounted for when we're trying to find out the hybridization, not delocalized. So these are delocalized. So can't be accounted for in hybridization. So that means that in case A, both of these are sp2 hybridized. So that also means that we have a conjugated pi ring system, just as an extra note. And we can count these 2 as part of the pi ring system. So we have 8 pi electrons here. So right away, we can cancel out options B and D, because now we know that option 1 must be included as well. So now the question is, do compounds 2 and 3, do they have 8 pi electrons? So let's look at these as well. So let's count the electrons at first in the double bonds, and now using our previous rationale, we know that these 2 electrons also have to be included. So now we're at 6. But now the question is, should we include this group as well? Well, let's draw another side view of that nitrogen molecule, right? So I'm just looking at this from an angle, and now we have this pair of electrons. And the thing is that there's already a double bond, right? A double bond between the adjacent carbon and the nitrogen. That does not involve the lone pair, right? That's important. So if there's already a lone, a pi overlap, a p orbital overlap between the nitrogen and another atom, then this pair of electrons, electron pair, is localized. So that means that it is accounted for in the hybridization. So if we take this as if we take that lone pair as an electron domain, then we have an sp2 hybridization, right? So here it is indeed sp2. So what this means, what this translates to for us, is that this is not a delocalized pair, right? So that means that it cannot be considered as a pi electron pair. So that means that 2 is not going to have 8 pi electrons, it's going to only have 6 pi electrons. And for the last case, for case 3, or for compound 3, we have, when we count, we have 4 from the double bonds, and here we have a heteroatom, right? So the thing is, we have to determine, well, we know that only one of these can be involved in the pi bonding. So we see that the question is, can this pair be considered? So when we look at this pair, we see that this is a heteroatom, and this also, you might think that there is the possibility of having the multiple cases, right? So let's actually entertain that. Let's think about that, right? So case 1, let's treat it as if we have we have 6 pi electrons. If we take into account these guys and we treat them as if they were part of the overall pi system, right? If we have 6 pi electrons, then that means that this sulfur is sp2 hybridized, and because this is no longer a localized pair of electrons, and so by Huckel's rules, it's cyclic, it's planar, and now it's conjugated, and there's 6 pi electrons, and a 6 pi pair of electrons. 6, you can get the number 6 if you do 4 plus 1 plus 2, 4 times 1 plus 2, and that gets us 6. So the 4n plus 2 rule applies. And so what does this mean? It means that for case 1, we would have an aromatic system. However, for case 2, right, if we don't include these guys, so if we take them off the map, right, if they're no longer part of the pi system, then we have 4 pi electrons. And 4, as you all know, is a multiple of 4. It just means 4 times 1. And even though we can't say, the problem is that we can't jump to saying that, oh, that means it's an anti-aromatic, because remember, one of Huckel's rules is that we need the system to be conjugated. And if both pairs of electrons are localized, then we have an sp3 hybridization. And if we have an sp3 hybridization, then the ring is no longer conjugated. So this translates to the fact that that Huckel's rules are violated, and so this becomes non-aromatic. So now let's consider the two cases, right? We have aromatic and non-aromatic. So remember the energy diagram, right? Which case will the system prefer? Will it prefer having 6 pi electrons, or will it prefer having 4 pi electrons? Or in other words, will it prefer having an aromatic system or a non-aromatic system? And since aromatic is lower, then we would obviously choose the aromatic system, right? So that means that in reality, this molecule will, even though it has two options, it will go towards the option where it has 6 pi electrons. So now we've found out the number of 8 pi electrons, and we see that 2 and 3 do not have 8 pi electrons. So that leaves us with just compound 1, and that gives us A as our final answer. For the next question, we have this compound where we have a benzoic acid, and we treat that benzoic acid with nitric acid and sulfuric acid, and we're asked to find the major product of this reaction. So this is a simple AES question. So this reaction is AES, so electrophilic aromatic substitution. And the reason why I say that is because, remember, we have a nitration mixture here. Nitric acid and sulfuric acid, and that produces the nitronium ion. which will basically interact via the ES reaction. And so what is important if we have the ES reaction, right? So ortho, para, and meta directors influence the location of substitution. So if we want to find out where this nitronium ion is going to actually land on the ring, we have to look at the substituent. And we see that this substituent is a carboxylic acid group. So we see that it is indeed a strong electron withdrawing group, and it's also a meta director. So if it's a meta director, then we have two possible places where it can land, right? So it can be here or here, right? So we would end up with, I'm just going to choose the one on the right. We have an equal chance, and they are both equal by symmetry, the final product that you get. You won't be getting a product where it has both sides occupied, at least a major product. So that means that we have this as our final answer, and it turns out that that is choice D. And with that, we have solved this question. For the next question, we have this polysubstituted benzene ring with 2 chlorine substituents and 2 nitrous substituents, and it is reacting with sodium methoxide, 1 molar equivalent of it. And the question is, what is the expected product of this reaction? So when we look at sodium methoxide, we realize that sodium methoxide is a strong nucleophile, very strong in the methoxide anion. So we realize that this is actually going to be a nucleophilic aromatic substitution reaction, or in other words, an NAS reaction. So unlike a ES, or electrophilic aromatic substitution reaction, NAS reactions actually get stronger, they go faster, the reactivity goes up as you deactivate the ring. Why? Because when you deactivate the ring, you make it more electrophilic. As you deactivate it. And the more you and since a nucleophile is attacking the substrate which is acting as an electrophile, the more electrophilic we can get that substituent, the better the reactivity is, right? So basically, the rules of the game are reversed now. So let me just note that down. It operates faster with more electron withdrawing groups. And in an NAS reaction as well, the role of a I'm trying to put this the right way. In an NAS reaction, ortho-para directors and meta directors do not play a role. So the location at which the nucleophilic substitution occurs is at the location of the leaving group. So when we look at our structure, what is the best leaving group, an NO2 group or a chlorine group? It's the chlorine group, right? So we know that one of these chlorines are going to be substituted. So it turns out that there are 2 commonly known pathways for a NAS reaction. So 2 pathways. Addition elimination and elimination addition. And I had touched on this earlier. So I said previously that this occurs at less harsher conditions. So, and it also it doesn't require a benzene intermediate. So the benzene ring with the funky triple bond. But that's precisely the case for elimination addition. And when we're dealing with the methoxy group here, it's going to undergo the addition-elimination reaction because it's also the preferred path. It's the elimination-addition reaction typically only occurs when you have strong bases like sodium amide or potassium or KNH2 or other specific reagents, and at much harsher conditions. So we're talking 340 degrees C, 2500 psi. So right now we're going to be focusing on the addition-elimination mechanism. So in order to really understand what's going on here, it's best if we try to consider this from a mechanistic point of view. So I'm actually going to show the mechanism for this. So for the addition and for the addition elimination pathway, the electron withdrawing groups, right? They help to accelerate the rate of the NAS reaction, but at the same time, the electron withdrawing groups, in this case the NO2 groups, they play an important role in determining which leaving group might be removed as well. So a requirement is that the leaving group must be ortho or para with respect to the electron withdrawing group in the ring. So right here we see that the NO2 groups, right? So if we consider their ortho and para configurations, I'm just going to clear this out. We see something interesting. So ortho for the NO2 group, let me just mark these in different colors so you don't get confused. So for this NO2 group, there's only one chlorine that's corresponding to this NO2 group, right? And for the other NO2 group, we see that the only chlorine that's corresponding to it in the ortho-para configuration is this one as well, right? Because here this one is ortho with respect to that chlorine, and this one is para with respect to that chlorine. So that tells us 110% for sure that this one is the correct leaving group. This is the one that will be substituted with by the methoxy group. So when we actually do the reaction, we find the following. So I just wanted to give the rationale for why we're going to attack that specific chlorine before we actually dive into the mechanism. And the NO2 group here. And so let's see. We have the methoxy group. And what this methoxy group is going to do is it's going to attack this carbon, and this double bond is going, the electrons of that double bond are going to migrate to the electron withdrawing group, and that's going to force these electrons up to this oxygen. And what we get is this, excuse me just a second. We're going to get the following structure. I'm writing OME to account for, to just make a shorthand version of the methoxy group. And now what's going to happen is we did the addition part, right? We added that methoxy group. Now the elimination part is going to occur. So one of these oxygens is going to give a pair, it's going to form a double bond with that nitrogen. That's going to push this pair of electrons down. Excuse me, I did not mean to include that there. Okay, right there. And this is going to push out our leaving group, the chlorine, and we are left with the following. And when we look at our answer choices, that gives us C for our final answer. For the next question, we have a compound with multiple rings, and we're asked which position will be attacked most rapidly by the nitronium ion when the compound undergoes nitration with nitric acid and sulfuric acid. So in this reaction, right, the reaction they're talking about is nitration, right? So it is an EAS reaction, and what occurs with EAS reactions, the more we can activate the ring, the better it will be, the more reactivity will be. Excuse me, when I mean the better it will be, I mean the more nucleophilic it will be. So we're trying to find the location where that NO2 group is going to go onto the nitronium ion, excuse me. So what this means is, if you remember from a previous problem in the FRQ section, the free response section, we had a similar scenario where one of the rings had one group and another ring had another group, and we were trying to see, well, where is the next substituent going to land on? And since this is an ES reaction, the most activated ring will be favored, right? So the most activated ring will be favored. And we see that for the ring on the left, we have this ketone, and it's actually, since the carbon has a partial positive charge, this is going to be an electron withdrawing group, right? So what that means is that this will be deactivated, and we see here that this is a simple methyl group, but it is an inductive electron donating group. So this will be activated, right? And in addition, since we also know that the methyl group is an ortho-pair director, so if it's an ortho-pair director, then it has only the following locations where it can land a site. And so now, since we know that the ring on the left is less activated than the ring on the right, we can just treat this entire thing as a substituent to this ring. So it will not have any it won't be useful in terms of reactivity. So when we look at our potential sites, right, we see that D is the only possible site out of the options that are mentioned in the answer choices that we have. So D becomes our final answer. Now we have reached our final problem for this review session, and we have the following question. For the nitration of bromobenzene with the mixture of nitric acid and sulfuric acid, which intermediate is used to explain why halogens are orthopair directors? So this is a very conceptually heavy question, and the first way we're going to tackle it is we have to understand what the real definition of an orthopair director is. So an orthopair director, so first of all, this is a, like I had mentioned earlier, this is an EAS reaction, right? A nitration reaction. And for an EAS reaction, the orthopara and the status of a functional group as an orthopair director or as a meta director will have a strong role in deciding where the next substituent can be added through an EAS reaction. So that means that for an EAS reaction, an orthopair director, I'm just going to write it down, will cause the carbocation intermediate in the EAS reaction to have its positive charge at the location of the director. So it's going to have it at the carbon that is attached to the director. So let's actually try to do this mechanism for this reaction, right? So from the mixture of nitric acid and sulfuric acid, we get the nitronium ion. And turns out that if we have this bromine group here, right, we know that it's an orthopair director. But for our purposes, for the final product, we see that it's para with respect to the bromine group, right? So let's let the first step in the ES reaction is, of course, the addition of that NO2 group, the nitronium ion. So what's going to happen is that double bond in the ring is going to go out. The electrons in that double bond are going to go out and form a new bond with the NO2. And what this does is that it has the following intermediate. So because we have, removed that double bond, there's a positive charge on a carbon in the ring. Now, since the bromine group has lone pairs, right, 3 lone pairs attached to it, it can actually engage in resonance. It can engage in pi electron donation. So this pair of lone pair of electrons will go down and it will form a carbon-bromine double bond, and that will force the pair of electrons on this double bond to migrate one bond downwards, and now we have this structure. excuse me, not that. And there's something really interesting here in that if you just simply move this pair of electrons back up, right, what do you see? You get another resonance form where you actually have a carbocation where the positive charge is actually on the carbon that is attached to the orthopair director or the bromine. So we have gone through the mechanism for this, but or at least the first step. And the first thing that should come to mind though is that when you are trying to understand which intermediate will show why the halogens are orthopair directors, you also need to consider energetics. So in this case, even like if we look at our answer choices, we see that choice C is here, and we see that choice D is also here. So the question is, well, which one is it, right? Because obviously A and B are already out, but which one should we choose from, C or D? Because actually these are just resonance forms, right? The same resonance forms that we drew on the right-hand side. So which one will show why the halogens are orthopair directors? So from our previous definition, we said that it should cause the carbocation intermediate in the ES reaction, the orthopair director, it should cause that to have a positive charge at the location of the director, right? But another thing we need to consider is that that intermediate needs to be resonance stabilized. So even though these two are resonance forms, the thing about halogens that really makes them suitable orthopair directors is that they can also take up that positive charge. There is that charge delocalization, right? You can delocalize the charge to that bromine, and that allows that bromine to contribute to be a major contributor to the overall resonance hybrid. And so this is actually a better picture for why the carbocation intermediate would be resonance stabilized, right? So if I was to make it more clear, it should cause it to be a resonance stabilized carbocation intermediate, right? So a lot of electron withdrawing groups, they might not allow for the same movement of formal charge as a halogen, right? Because a halogen has all these additional lone pairs that allows it to contribute to a significant resonance form, and it also allows for the delocalization of positive charge to the director itself. So this is the best portrait of why this is an orthopair director. I know this was a rather conceptually heavy question, but I would highly recommend that you guys check out the online resources about what makes a site a orthopair director and a meta director. That's a whole nother concept as well. I would highly recommend the source Master Organic Chemistry. If you just go on Google and type in Master Organic Chemistry, you will go to a website where there are a lot of blogs and information posts about all these topics that we covered today. And so I would highly recommend that as additional study material for your upcoming exam. And with that, we have finished our review. And I hope this was helpful. Best of luck with your exams.